A 0.5 farad capacitor is in series with a 2 ohm resistor. How long does it take a 5 volt ideal battery to charge the capacitor to 2/3 its full capacity and 99.9% of its full capacity? Let's begin by sketching the circuit. We have an 5 volt ideal battery that is in series with a resistor and a capacitor. The resistor has 2 ohms of resistance, and the capacitor is a 0.5 farad capacitor. We want to know how much charge is on the capacitor plates when it reaches 2/3 of its maximum capacity and 99.9% of its maximum capacity. To solve, let's look at the relationship for the charge on the plates of a capacitor as a function of time for a charging circuit like we have here. The charge is given as the product of the EMF of the battery and the capacitance of the capacitor times 1 minus e to the minus t over RC, where the product RC of resistance and capacitance is called the time constant. Here we see that the product RC is equal to 1 second because 2 ohms times 0.5 farads is equal to 1 second. Now remember, that time constant is the time it takes for the charge on a capacitor to reach about 0.67 of its maximum charge. Well, since for part A we want to find Q when it's 2/3 of its maximum charge, we can surmise that our answer should be about a second. So let's go ahead and look at this. One thing to recognize is this coefficient, the product of the potential difference of our battery and the capacitance. This coefficient, remember, corresponds to the maximum charge of our capacitor. And that takes place after a very long time, essentially when t goes to infinity. This means that we could express the charge as a function of time to be equal to the product of the maximum charge on our capacitor, so that's the capacitor at full capacity, times 1 minus e to the minus t over RC. Our goal is to solve for time, how long it takes Q to reach 2/3 of the maximum. So let's isolate the time out of this equation. To do that, I'll divide both sides by the maximum amount of charge to be stored by the plates of our capacitor. So that's going to be equal to Q over Q max. This becomes e to the minus t over the product of the resistance and capacitance is equal to Q over Q max minus 1. Let's distribute the minus sign by multiplying both sides of this equation by minus 1. To solve for time, let's take the natural log of both sides of our equation. That natural log will remove time from the exponent of the exponential. This becomes minus t over the product of RC times the natural log of e is equal to the natural log of 1 minus the ratio of charge on our capacitor plates to the maximum charge of our capacitor at full capacity. The natural log of E is just 1. And let's multiply both sides by minus RC. So the time is equal to minus the product of RC, which is our time constant. Remember, for this circuit, that is going to be equal to 1 second, times the natural log of 1 minus Q over Q max. So here is an expression for time that is really a function of the charge on our capacitor plates. Let's use this expression now to find the charge when our capacitor is 2/3 capacity, and then when our capacitor is at 99.9% of capacity. So when our charge is at 2/3 of our maximum capacity, we could replace Q in our expression for time by 2/3 of our charge at maximum capacity. The Q max in the numerator cancels with the Q max in the denominator. What we have is the time is equal to the product of RC, the time constant, times the natural log of 1 minus 2/3, which is equal to minus RC, the natural log of 1/3, which is just minus RC, the natural log of 1 minus the natural log of 3. The natural log of 1 is just 0. We have a minus times a minus left over, that's a plus. So the time is equal to RC, the time constant, times the natural log of 3. So what this says is that the time to reach 2/3 of full capacity will be equal to just a little bit over the time constant. So let's go ahead and plug in our numbers now. Remember, the resistance was 2 ohms. The capacitance is 0.5 farads, and we have the natural log of 3. So plugging this into our calculator, we have 2 times 0.5 times the natural log of 3. And our answer to one significant figure is equal to 1 second. So it takes about a second for our capacitor to reach 2/3 of its charge at full capacity. And remember, that's what we expected. We expected that because our time constant, the product of RC, is the time it takes for a capacitor to reach 0.67% of its full capacity, approximately. 2/3 is pretty darn close to 0.67%. So the time being similar is fully expected and is a good reality check for us. Now let's find how long it'll take for the charge on our capacitor plates to reach 99.9% of its maximum capacity. So we could say that Q is equal to 0.999 of Q max. So the time is equal to minus the product of the resistance and capacitance times the natural log of 1 minus 0.999 0.99 Q max over Q max. So the charge at maximum capacity in the numerator and denominator cancels. And we have then T is equal to minus RC times the natural log of 0.001. So the time is equal to minus 2 ohms times 0.5 farads, which is 1 second, times the natural log of 0.001. Plugging this into our calculator, we get minus 2 times 0.5 times the natural log of 0.001. And to one significant figure, we get 7 seconds. So what this says is it takes 7 seconds for our capacitor to reach 99.9% of its full capacity. And that's an interesting result, because it takes only 1 second to reach 2/3 of the capacitor's maximum capacity for charge, while it takes an additional 6 seconds to go from 2/3 of the maximum charge to almost full capacity. That last 1/3 of charge to reach full capacity takes 6 times longer to reach than the first 2/3 of charge. This is a great illustration of the exponential nature of accumulating charge on the plates of a capacitor.